this started. Welcome everybody. Good morning, good afternoon, or good evening, depending upon wherever you are. Welcome to this week's rendition of the point distribution webinar. Today we have speaking Damir Ferizović, who is identifying as from the Graz University of Technology, talking about the spherical cap discrepancy of heel fix points. As a reminder, after the talk, there will be tea time to just socialize for anyone who wants to stay on. Damir?
Thank you, Ryan, for this rather weird introduction. Thank you for inviting me. So hello, everybody. So as you have heard from Ryan, I'm still at TU Graz. I'm a postdoc now, and I will be a postdoc at KU Leuven starting September. But for 2 more days, I'm associated with Graz University of Technology. And that's also the reason why as Ryan put it, I identify myself as TU Graz person. Anyway, today I'm going to talk about heel fix points, and I tend to present you the idea for a proof on the spherical cap discrepancy. So this is a joint work with Julian Hofstadler and Michel Mastriani. And I guess I would like to start to introduce them a little bit more, since they are PhD students. So Julian Hofstadler is right now already with Daniel Rudolph, who is at the University of Göttingen. So unfortunately, Julian will leave the field of point distributions and move to quasi-Monte Carlo stuff. Michel Mastriani is a PhD student with Dimitri Bulik in Minnesota. And so just in case you have some trouble money left for whatever reason, she would be happy if she would receive an email or an invitation to a conference, or I don't know, if you have some ideas to collaborate. Now, anyway, let me first start off with the spherical cap discrepancy. And it's, I guess most of you have heard of it, but just as a small reminder, a spherical cap is always essentially the intersection of the unit sphere with a ball of various radii. And it can basically be written as this inner product, as pointed out there. In the image to the right, you'll see this the boundary of the spherical cap. And it's not clear really from this picture if the spherical cap has a small diameter or a big one, right? Because the spherical cap and also its complement are spherical caps in this notation. Now, the thing what we are going to do is we are going to regard point distribution on the sphere. And the idea is always, okay, if you take a spherical cap and you distribute points on the surface of the sphere, right? Now, count how many points fall into your spherical cap, divide by the amount of points, and then subtract the area of the spherical cap. And what you obtain is essentially a measure how well distributed points are. This is the first definition. It's the local spherical cap discrepancy, right? You have just a fixed cap, and then you distribute points of ever larger amounts. And in the limit, what you should obtain is 0 if your points are well distributed. And of course, in this is the notion of asymptotically well distributed. What you then can do is you regard the supremum. So for every n, you just go through all the spherical caps and see what is the worst approximation to the area, right? And the reason why people want to do this often is attributed, I believe, to an integration error. So in this case, for the unit cube in the dimension. So assume you have a function of bounded variation. So it's not really important what this means. It just depends on the function itself. And then you distribute points in your unit cube. You take the sum and then the arithmetic mean. And again, you compare it to the integral of f, right? And this absolute value of this difference can be bounded actually by the discrepancy of the point sets times the product of the function. And that's a pretty neat property. So if we have a point set that has a decreasing discrepancy, then you will know that the integration error will go to 0. And of course, you also have an a priori bound, how fast it shall go to 0. And the reference for this is Funktionen von beschränkter Variation in der Theorie der Gleichverteilung by Edmund Hafka, 1961. So the question is, of course, how well can you distribute points on the sphere? And there's this result due to Beck that says, okay, there are actually point sets such that the discrepancy can be bounded above by n to the -3/4 times a log factor. But he also has shown that, okay, you cannot go less than n to the -3/4, and these constants are independent, just depend on the dimension, I believe. Also, that is valid for all spheres of various dimensions. And the proof for the upper bound has been probabilistic in nature, right? So there are certain point constructions that actually achieve this discrepancy with high probability. But the question is, of course, okay, can you construct actually a deterministic example? Can you give me an algorithm to produce points that has a very good discrepancy, right? And there's actually very little known on this. I believe the first result in this direction was due to Ferizović, Phillips, and Sarnak, where they have introduced some kind of alphabet and rotation matrices, applied it to one point of the sphere, and then they have been able to show that the discrepancy is something like n to the -1/3. And there's this paper by Sletner, Brochet, and Dick, and where they have actually shown that IID random points are of order n to the -1/2, again, up to constants. The quite famous Fibonacci points sets are upper bounded by n to the -1/2. So numerical experiments indicated that it's much better and actually closer to Beck's upper bound. But of course, that's not a proof. And there's also a proof by Okoye-Taiwo on a certain diamond ensemble where she shows that spherical cap discrepancy again is of order n to the -1/2 up to constants. So the aim of this talk, and actually the paper behind it, is that we regard this quite famous Hilpik's algorithm and show that the spherical discrepancy again is of order n to the -1/2. So it's lower bounded and upper bounded by this asymptote. So Hilpix, it stands for hierarchical equal area and isolatitude pixelization, and it's best explained by pictures, I believe. So the left-hand side is the thing you start with. You patch a sphere into 12 pixels, rectangular shapes. They're again all of equal area, and then you can increase the level or how fine the tessellation is supposed to be. So on the right-hand side, we go to level 1, right? And it behaves, each patch, each rectangular shape essentially behaves like the unit square. So we can now cut it into 4 pieces. Each one will have equal area, and we can bisect even further. And the really nice thing is, I mean, it's tessellations of the unisphere. There are a couple of those out there. I believe Paolo Leopardi, we had him in this webinar. He introduced one 2 decades ago, I guess. And the thing is, most of these tessellations have a spherical cap at the North Pole and the South Pole, and then you place rectangular shapes around it. So, of course, now these satisfy the properties that you usually need. So the diameter goes to 0, the areas are all equal. But again, there's something unsatisfactory, in my opinion, at least, if you have a spherical cap, right? Because it's not really a way how to bisect it somehow. So when I first encountered this Hilpix algorithm, a couple of years ago, so I thought, okay, that's pretty nice, right? Because there are many constructions on the unit square that you can do. I don't know, box dimensions, where you use boxes, you divide things. And the main idea basically is you can control, okay, if you cut it in half, you know, you have equal area, right? And these things you can essentially lift now without effort to each patch, and perhaps with some effort to the whole sphere. And that's, I believe, something that's rather interesting. So the paper that's cited down there by Gorsky, Hyvan, Bandelt, Hansen, Reinecke, and Bartelmann has been cited a couple of thousand times. And this Hilpix algorithm has been used in astrology and astrophysics, right, to essentially to cartography the night sky, if I'm not mistaken. Now, this Hilpix tessellation also introduces points, right? Because what you can do is you just place centers at each of those pixels, and the center is just the intersection of the final of the level of the grid, which has a level which has one level finite tessellation, and that's essentially how you distribute points. And yeah, I guess it's pretty simple, right? Now the thing is, okay, how do you draw these lines? So what's the algorithm? And it's a bit complicated, and I don't want to get into all the details, right? I'll show you some of the easy parts actually, and so such that you have an idea. I mean, on the whole description will be in our paper, but again, the thing it's sometimes more useful if we actually can just use a description and then code it and plot it the way that I did. So what you do is you have to cut your sphere actually into three parts. You have then a northern part, an equatorial belt part, and the southern part. So the northern part is essentially just a spherical cap with a certain height. And then for each of these three regions, you can describe your lines and how they behave. Now, the equatorial belt is the simplest to describe. So you take your capital letter L, which is 2 to the level of tessellation. And then you immediately obtain many intervals of length pi half. These are the I to the power L and J. And then you define these linear functions, which map always to the interval 0 to pi half. Once these functionals are defined, you can define lines. We will say, okay, the cosine of theta is always 2/3 minus 8/3 pi, and these functions, right? And so these lines, what it really means is you use your standard parameterization of the sphere. You have cosine of phi, sine of theta, where theta is again the arc cosine of the right-hand side that you're regarding actually. So MEJL, this just means essentially, okay, we draw lines that then go from north to south, right? That's the minus in front of the phi, and the P is actually a plus in front of the phi, but it starts in the south and goes up to the north. So this describes you all the lines that will appear around the equatorial belt. And perhaps you can see it, they're sort of like a arc cosine shaped, right? On the left-hand side, it looks like this. And then the finer the tessellation, the more arc cosine shaped curves appear next to each other. Okay, now the Hilpix algorithm in the paper by Gorski et al. Also comes with a map. So you have a projection from the unit sphere to the plane. And what we are going to show is also that it basically is area preserving. So that's pretty neat. And all these Hilpix pixel or Hilpix center points will be actually mapped to a lattice. So that's also very nice. And I'll show you basically all of the projection map. So if we are in the equatorial belt, so that's the height, right? The Z value is between -2/3 and 2/3. Then the projection map is given by this gamma of x, where it maps the x value is just phi over pi, where phi in this case is just the parameterization of x, right? With the standard parameterization that we had previously seen, right? We have this phi and theta, and that's exactly what we plug in here. And then, of course, then you regard the northern cap separately and the southern cap separately, but there is no real difference, right? It's pretty symmetric, and everything below the northern hemisphere is just a sign change in the Z value. Okay, so the first thing I want to tell you is, okay, that this projection map maps each of those curves into straight line segments in the plane, right? So what you have what we have here is the gamma of now the equatorial belt, the curves that go from north to south, and the representation is exactly what you see on the left. It's x values phi, y values -phi plus a constant, and it's of course a linear function. The same thing also for the curves that go from south to north. And then, of course, you plug in all the definition for the curves in the northern and southern caps, and you will see, okay, what you obtain again lines. And the thing in the picture you see below is again the projection gamma. So I have this Hilpix tessellation, I believe, of level 2, and now I map each of these curves and also this hemisphere into the plane, and we see here the characteristic image. So the image of the sphere under gamma is not a rectangle. It's this zigzag-shaped object that we see here. And what you should really think of is like each pixel, base pixel is mapped to a square of a certain length. And then since we have 12 base pixels, we have really 12 squares placed on each other. So on the top we have 4, then around the x-axis we have again 4, and then below again 4 further. You see each subdivision of these pixels again is mapped to squares in the plane. And this already is basically a proof that the projection gamma is almost area preserving. So what do I want to tell you? So just imagine you have an open set placed on the sphere, and now you have your tessellation, right? And you can map the open set via gamma, and you map, of course, the tessellation. And what you can do is, okay, you count how many subpixels are inside the open set, how many fall directly into the interior. And then, of course, they're mapped to the interior of the image of this open set. But again, so each subpixel on the sphere has equal area. Each pixel that's mapped has equal area. And what you count is, okay, the same amount that are in the interior are mapped to the same amount that's interior in the image. And the same goes for also for a cover of this thing. So what you obtain is, okay, you have basically the same amount of pixels inside and covering it. It's just that the image of each pixel, that the area on the sphere is not the same as the area on the plane when you map one of those pixels. In other words, sorry, we have following result. So if you have a base pixel B, right, and then you take an open set, then you have the area of A divided by the area of B is the same as the area of the mapped element divided by the area of the mapped pixel. And that's what you obtain. So that's pretty neat. So the next image that you see is again just the Hilbig's points in this case, and then we map them via gamma, and here we can directly see that it looks like a lattice, and the D is basically a Z2 scaled and then shifted by the vector 1, 1 over 2n, if n is the scale. And that's also unfortunate, but the true fact that you don't really have a convex mapping, right? So the first time I was dealing with this Hilbig's algorithm, I was very convinced that the interior in each base pixel of those maps of spherical caps, right? You regard which part falls into a base pixel, you map it via gamma, and what you should obtain, I thought, was basically a convex set, because the left-hand side is something like geodesically convex. But unfortunately, that's not true. And what you see here is the picture of this spherical cap that encapsulates the North Pole, but passes by close by. And what you see is, so each of those 4 peaks is essentially the North Pole. So it's not a bijection, but almost, right, except for the North and South Pole. And what you see is that the boundary of the spherical cap gets bent upwards. I mean, it's no contradiction. It always preserves the amount of pixels that are inside, but still, it's just because of the projection that it's no longer convex. But okay, the theorem that I actually already mentioned at the beginning is, okay, we can show that the spherical cap discrepancy of these Hilbig's points is of order n to the -1/2. So up to this constant, they are more or less guessed, because truth be told, we have not really computed them yet. We know that the lower constant is something like 2 over square root of 3, and the upper constant perhaps something close to 500. So we have to check this yet, but I mean, it's not that important. The important thing really is that the orders of this type, and I'm going to tell you how to prove this really. And the thing is, we are going to recycle ideas of Weisleiter and Brauchart and Dick. And what they did is, okay, they had a special projection, the Lambert map, which is area preserving. So they mapped each spherical cap from the sphere to the unit square, and then they regarded the curvature of the mapped boundary. The thing is, you will need the zeros of this curvature in order to cut your image in order to approximate it a bit by the isotropic discrepancy. But before I go ahead, let me just introduce what this notation means. So the boundary of the spherical cap is just given by those phi and theta that satisfy this relation. This is just a very simple text, right? You have this inner product, you take the standard parameterization, you write out what the inner product means, and then you use this angle sum formula for the cosine. That's how you obtain this equality for the boundary. And now, if sine of θw is not 0, you can solve for phi, and that's exactly what's done down here. So you have two solutions basically, which describe always 1/2 of the boundary of C, right? So you would have technically dealing with two things, but since they're very similar, except for sine, there's really no need for this. And this is just the description of the boundary. And again, we map the boundary now by gamma and calculate the planar curvature. And actually, we try to find its zeros. So the thing is, you have to exclude certain cases, right? Because the spherical cap that's centered at the North Pole or at the South Pole, the boundary gets mapped to a straight line. And that's actually where the lower bound for the discrepancy comes from. This is this special case where we actually can see, okay, you have certain, straight lines, and they just take a lot of points, too many points, and contribute essentially to this discrepancy bound, the lower bound, right? Because that's, you have to do worse than these special spherical caps. Okay, and then the notion of a pseudo-convex set is really important here because that's how you're going to cut it. Now, pseudo-convex set, just to give you the definition, so the set A, right, this is the pink thing, is called pseudo-convex if you have p many convex sets such that the intersection always is empty. A is covered by those convex sets, and then either the convex set is a subset of A, or the set minus A is again convex. So just to picture what this means is, okay, look at this this picture. So if we start on the local maximum on the left at A1, we go down there, down the boundary, and then we hit a spot where we have essentially zero curvature, right? It bends in outward after a while, and then there is a zero of the curvature, and here we make a cut through the set, which is axis parallel, we just cut it off. Then we follow the boundary further, again to a zero of the curvature. Here again, we make an axis parallel cut through the set, and then we follow along the boundary, and we don't detect any zeros for the curvature. So what we have done now is, okay, we know A1 is convex, A3 is convex, but the part of A that's pink and A2 is not convex anymore. But we can construct a convex set either by just considering the whole strip, or in this case, I just connected the zeros of the curvature. So A2 is now the whole strip here, which contains a part of A, but is not a subset of A. And A2 is clearly convex, and A2 minus A is now this white part, which again is convex. So this is a pseudo-convex set. And that's clearly the reason why we need to calculate curvatures, or actually the next lemma gives the reason, because Eisler, Abraham, and Dick proved the following theorem. So if you have a point set Pn in your convex set A, or pseudo-convex set A, then you can bound the discrepancy of this pseudo-convex set by 2 times P minus Q times the isotropic discrepancy. That's what the Gn means on the right-hand side. So 2P, P is again the number of the covering that you regard of these convex sets, and Q is the part of sets falling actually into your set A, right? Now, the isotropic discrepancy is again a discrepancy in this time in the unit square, where you regard the just convex sets, right? Same thing as above. Okay, you have a point distributions in the unit square. For your test set, you just take any convex set. You count how many points fall in the convex set. You take the arithmetic mean, and you compare to the area. And what's the worst what's the worst that you can produce amongst all convex subsets? So this now helps us to again copy paste the results or the methods in isolate number technique. So we have our spherical caps, we have our projection gamma, which is area preserving almost. And then we map the boundary of the spherical cap. We see, okay, it has finitely many zeros for basically most spherical caps. At these zeros, we cut our set into pieces. We cut the image of the spherical cap into pieces that are pseudo-convex, or actually we form a pseudo-convex set of it. And then we know, okay, for this thing, we can bound this the cap and discrepancy by the isotropic discrepancy. And so all we now have to do is find the isotropic discrepancy for the convex sets for the Hill fixed points, right? But that's very easily obtained because we deal with a lattice. And this, I believe this result is known or appears in most books, wherever. So if you have a convex set and you have your lattice, and then you want to count how many points fall into it minus the area, you will know, okay, the only thing that contributes to the discrepancy are these boxes of your lattice, these fundamental cells that intersect the boundary. And since it's a convex set in the unit square, it's bounded, the length of the boundary is bounded by 4, right? That's the best you can do. And then you immediately obtain this bound that you have essentially the amount of points falling into a convex set normalized by n minus the area is always less or equal to 4 than n to the minus 1/2. Again, 4 coming from the boundary. And if you take the supremum of all complex sets, this will of course not change, and this gives basically the upper bound. All we have to do is now count, okay, how many convex pieces do we really need to cut up the images of our spherical caps and the gamma, and then we obtain quite a big number. And again, the lower bound is obtained just take special cases like the northern hemisphere. The boundary is mapped to a straight line, and along the straight line you obtain square root of n many points. So that's really the order of this spherical cap discrepancy. And here my talk concludes. So thank you very much for your attention, and I don't know if you have any questions, please feel free to ask me.
Any questions for our speaker?
So I have a quick question. So Damir, thank you for your talk. So it feels like the proof that you gave actually. So what it means is that you have bounded the discrepancy not just with respect to spherical caps, but so maybe convex sets or something. So is that the case? So it feels like it's more general than just spherical caps, what you do here. Is that a correct impression?
I mean, the thing is, we can basically show, because of the definition of this projection map gamma, and that spherical caps are mapped into sets, they can be covered by a most finite number of convex sets, say 16 or 20, right? Mm-hmm. And that's the thing. So it's not that general, right? I mean, if you want more general sets, you might have to increase the number of convex coverings, and then the constant gets higher and bigger, right? It's just that we have shown, yeah, the image of circle caps can be bounded, can be covered by at most 20 convex sets. That's
okay. But is it the correct intuition that, okay, maybe a similar statement is true for, you know, some reasonable convex thing, and you map it through gamma, and you get pseudo-convex maybe messing up the constant a little bit.
Yeah, sure. I mean, if you can show that it's bounded, no matter what, right? It's fine. I mean, you need a bound for all tests that you include, of course, right? And that's what we do. for each spherical cap, we can show okay, it's bounded by 20 pseudo-convex sets, 20 convex sets. That's it. That's all. If you change your test set, of course, you need to show that you have a bound. Otherwise, you cannot really argue.
And this bound of 20. So do you have to do it somehow separately for this equatorial belt and then the?
Yeah. So what we have been shown is okay. Look, you regard these spherical caps that are not somehow singular, right? Where the map gamma doesn't project the boundary to straight lines. And then you obtain an equation for the curvature, and then you can say, okay, if the planar curve, right, the map of gamma partial C belongs to the equatorial belt, then you will see, okay, there are at most 4 zeros there, right? If it belongs to the north or the southern cap, again, at most 4 zeros there, or 5 zeros, right? And then you know, okay, so you have a spherical cap, which goes essentially, could go from the north to south, right? Close to the North Poles, essentially, just going through all the belts. Then you have to sum up, of course, for each of those, there is at most 4, and then you have, or 5, and you sum up to 20, because you go to four regimes, and that's it.
I see. Makes sense. Thank you.
Okay.
So there is a question in the chat, and I wanted to ask about that also. So there is a question from Carlos in the chat about the lower bound.
Yeah.
So, yeah, can you say a couple of words about the lower bound, and then I may have some follow-up questions to that.
Sure. I mean, you see this picture, right? So what you see is the hemisphere lightly tilted, so the center is not the North Pole. But you see already how flat the curve is, the mapped curve, right? And now just imagine, okay, if the hemisphere now is centered at the North Pole, this curve becomes just a straight line. And because we have now essentially the lattice zeta2, this straight line will pick up many points, right? If you have n many points, it will pick up 2/2/3 square root of n many points. That's it. And now if you make your hemisphere a little bit smaller, you lose all those points without changing the area a lot. And then in the supremum, okay, you can just consider those spherical caps. You can say, okay, the area doesn't change a lot, but all of a sudden you have this jump in 2/3 square root of n many points, right? So this gives the lower bound. It's just that it's a very bad cap for these purposes because there's so many points on the equator.
Do you know if this is the only bad cap, or are there?
No, there are also. That's just the burst, as far as I see. And what you also can do is you take a spherical cap centered at the equator, anywhere at the equator, but make it again the hemisphere. And then you have the problem that your spherical cap goes now to the North Pole and to the South Pole. And what you get, what this is mapped to is just 2 vertical lines, right? And again, you pick up many points on these vertical lines if it's adjusted correctly, right? But again, the worst thing is,
yeah. So a couple of questions then about your upper bound. So first of all, do I understand it correctly that it's important how you construct these pixels, but it's not really that important for the upper bound how you choose the point within each pixel, right? Is that correct, or is it important that you choose specifically the centers?
For this upper bound, you mean?
Yeah, for the upper bound.
No, it really doesn't matter. I mean, that's actually a small remark, because what you can do is you just essentially take every lattice, and it should still work, right? But of course, if you take a different lattice, then you lose a lot of properties, right? You don't know how many points.
No, I'm saying assume you already constructed the tessellation. The tessellation is there.
Yes.
So the picture is like here. But then, okay, we need to choose the points. So you choose the centers. What if I choose the points somehow arbitrarily within those pixels? So I choose the points.
But then you have jitter sampling, but that's...
No, but okay, not randomly. I'm not taking any expectations or anything, but I just say, okay, some fixed, I'll get to the jitter sampling, I'll ask that.
Okay,
but,
sure.
Right now, let's choose something which is not the centers. Within this, you already have this tessellation, but if I just choose other points somehow
Yes.
in an arbitrary way. Do you still have the upper bound, the same upper bound, or was it crucial that you specifically take the centers?
No, the upper bound is just the image that you see here. Just give me a moment. Right? Because if the points are in each pixel, right, then you can always argue the same thing. Okay, the area is basically
Right. Yeah.
the same.
So that was good. So it was not important that the points themselves form a lattice. It was important that essentially the boundaries of the pixels, right, are
Yes.
formed. Okay. Yeah. So that was my question.
Okay.
Okay. And then a follow-up question. That's something we discussed yesterday with Michelle. You can do jittered sampling with this same thing, right?
Mm-hmm.
And then if you choose random points inside these pixels, then with good probability you will have almost optimal discrepancy, right? And
yes, but that's I believe the proof of Matuszek, right?
So jittered sampling here works the same way, right?
Exactly.
Just because you essentially have all the properties that you need. You have an equal area partition.
Yes.
Well, almost equal. Yeah. Okay. Yeah.
No, it is equal area.
Yeah. Okay.
But I don't. I mean, do you think that's interesting, right? I mean, that's just Matuszek's proof of a different tessellation.
Yeah, for a different tessellation. Well, I think it's something worth maybe worth mentioning.
Okay.
Okay.
Okay. Thank you for the question.
Also, so sorry. One more thing. I recalled while listening to this that I've seen a similar tessellation, but much simpler in structure. I've seen some picture of it. If but I don't know if it's interesting, if it's used any. This one is actually used in astrophysics, the one that I've seen. So if I can share the screen for a moment.
Then I have to stop. So let me perhaps stop. Okay, is this okay? I'll stop sharing, and I don't know if I will get it ever up again on the screen. Okay, there we are.
So, but that somehow reminded me. So let me share the screen. Okay. Yes, I think. Do you see my screen?
Yes.
Yeah. So this picture here. So basically, what you do, I don't remember where I saw this.
But it's just a unit cube.
Right. You take the unit cube, project it onto the sphere, and divide it into subsquare. It divide every face into subsquares and also project it onto the sphere. So that's
but that's not equal area anymore. It's not equal area.
No,
right?
you can do it. You can choose. You can choose the subdivision so that it's equal area.
And do you think that's simpler? Seems a bit.
I don't know if it's. I think it's at least intuitively it's clear how to do it. But I'm wondering if you can. If for this tessellation you would get the same bound, probably you would, right? Probably it should be possible to get n to the -1/2 for this tessellation.
I mean, it depends on the projection. I'm not quite sure how.
Right. Yeah. Here probably it's easier to envision what is happening, but it's not clear that it's easier to write the projection down. Yeah. It's probably going to be more complicated. Anyways, it just sort of reminded me that.
But I believe the same problem should also appear. So if they're again centers of the pixel, right? Then you have a hemisphere where you map essentially the four.
Right. Yeah. I think if you take centers here, you will run into the same thing, because you will have a lot of things along the same lines, which could be boundaries of spherical caps. Okay. All right. Yeah, and the last question is, what if you take if you restrict yourself to spherical caps that are strictly much less than the hemisphere, so aperture pi over 4 or less, would you still run into these problems?
Of course, yes. The same thing applies. We always place the center at the North Pole or South Pole.
Okay.
And then it's always
okay. Right. Yeah, sure.
Map to straight lines, and then of course you have smaller values. But
of course. Okay. All right. Yes. So sorry for intruding with the picture.
No, it's fine. Thank you.
Hello. So might I ask the next question?
Of course, as many as you want.
Basically, I'm always asking this question if someone gives a talk at a sphere. So maybe I already got an answer and forgot it because I was not satisfied. But what is the reason for taking a construction that at the end has something like a North Pole and a South Pole? So because the whole problem that you have is some kind of symmetric, right? And now you say you have a construction, there is a North Pole, there's a South Pole, and all the time you have problems with the pole, right?
Yeah.
Is there some way of maybe using more than one of these point sets centered at a different North Pole or something like that, just to eliminate the problems of this kind?
I'm not sure. I'm quite sure what you mean, to be honest. I
So
mean,
the spherical caps. So the spherical caps, you don't only take the caps at North and South Pole, right? You take all.
I take all. Yes, yes.
Of course, yeah. But now at the end you have a point set where you identify a North Pole, right? That's completely random. That's a completely free choice.
Yeah, sure. Okay, okay. Yeah.
Okay, yeah. And at the end, if you have problems with the North Pole and the South Pole, then these are self-made problems to some extent, right? That's just a problem.
I don't know that they are. I mean, how the thing is, if you take the sphere and you want to talk about the sphere, right? Either you do it intrinsically, or you really just put a parameterization. But once you put a parameterization, you have the North and South Pole always. The only way that I know you can avoid this is just IID random points. Then you precisely have no orientation, so to speak. But what do you do with those things? I mean, you want a deterministic algorithm, and if you have an idea how to place points actually without so it looks essentially the same for every direction, then this is a valid paper on its own. So again,
but you could take the union of 100 of your point sets where you take the rotation also kind of.
Yeah,
equally.
but
or you could probably do something like that. Start with a point set, and so construct this point set where you have a North and a South Pole, but then use every point of that set to construct a new one with this point as the North Pole, and then take the union, so you'll have n squared points.
Sure,
yeah, actually that's interesting. So this could eliminate the problems with the South and North Pole, because now the number of points that you have on the equator is going to be quite small compared to the total number of points.
I mean, the thing is, what can you say about those points, right? And just because you center them at those points, it doesn't mean they're well distributed anymore. Because now you have the two things that you essentially rotate. Now 2 points or many points can be very close to each other, right? And some region stays empty. And now, are you able to show something in the asymptotics, right? I mean, it will be asymptotically uniformly distributed because each of those things is.
Right, because each of them.
But
yeah, it's not clear that you'll still get good discrepancy bounds.
Exactly, yeah.
That's an idea. Yeah.
I mean, look even at those points, right? I mean, Hilpik's very beautifully distributed. Still, discrepancies like random points, right? And now you say, okay, you do something weird with it, and I don't know if you will be able to show something. I mean, of course, it's interesting to tackle this and take a look, but still, I don't believe it will help, right? Because you will then have many directions that are close to each other, and then the spherical cap might again catch a lot of those things again, just because you have now mapping of straight lines. So.
Sure, but at the moment your problem is really the orientation that you fixed yourself, right? All the lower bound and all the things you said are basically based on the orientation you chose yourself, right? And I don't say that taking a second one or something, or taking more of them does not mean it's better, right? At least you have different problems. But maybe these other problems are easier to solve, right?
Okay.
Because you already know that there is no hope to work more with precisely this construction just because of the reasons you told us, right? You have a lower bound on the discrepancy and an almost matching upper bound.
I mean, what you also can do is just shift the levels a little bit and the problem goes away. It's just the problem that straight line that's mapped catches so many different lattice points.
What do you mean by shift a little bit?
Well, the lattice is essentially zeta2 rotated with 45 degrees. So you have on many points essentially on axis parallel lines, right? And if you just rotate it, that's what I mean, sorry. Rotate the lattice a little bit, you won't have that many points on your mapped boundary.
Could be, yes. I don't get it.
This is, I mean, I can perhaps show it to you if you like. me just see if it works. Yeah, it looks like it works. Where are those things? Yes. So if you see the right-hand side, right, that's what you obtain. That's
Damir, can you rotate it so it's in landscape mode, please? Thank you.
So the right-hand side is just a map of the Hilbig's points, and you clearly realize it's a lattice, right? And again, the problem is for straight lines that are axis parallel because they get many points. But if this lattice that you have on the right-hand side, you just rotate it a little bit, and all of a sudden there won't be too many points on axis parallel lines anymore. I mean, of course, there will be other lines, but that's not a problem because you obtain only straight lines if you map the boundaries of the North Pole caps or the hemispheres represented at the equator. And those are gone just by a simple rotation, a small rotation, right? But of course, you lose a lot of properties. You have now no longer control about the points. You don't know if they're in pixels, how many are in the pixels.
But what do you rotate? Sorry. What do you want to rotate your point set, right?
Yeah, I mean, in
but
the plane.
But then I can just also take the rotated spherical cap, and you are back in the problem again. So at the end, you are taking a supremum over all the boxes, and you told us that there is a fixed, not boxes, all the caps, and you told us that you know what is the worst cap, and I just say just try to avoid this bad cap, right? And I don't see any solution to that except destroying this kind of orientation. But I don't know if it works better. Most likely not.
I'm not quite sure what you mean. So if I regard the lattice in R2, right, the right hand side, I rotate it a little bit, and the points that I obtain I map back by gamma on the sphere. And why do you think that there's another cap that will have the exact same?
Can I interject? I think I understand what the confusion is. So there's two different, in a sense, lattices going on here. There's the how the points are put down, the actual points we're looking at, and then there's the lines that make the Hilbig's tessellation.
Yes.
In a sense, the projection, everything that goes with it. The projection, the lines that make up the Hilbig's tessellation, that's not changing.
Yeah.
What Damir's talking about is just rotating the lattice of points. So in a sense, the reason he was running into an issue is because of when you do this projection with certain spherical caps, you're going to get straight lines. And that's when they're centered at the North Pole or when their hemisphere centered at the equator. And so in a sense, by moving the points a little bit by rotating, but keeping the projections the same, the points no longer line up with the straight lines. Whereas right now with the original way that they're doing it, they do line up with the straight lines, and that's why it's causing a problem. So yeah, just rotating the point set. If you imagine the lattice in the whole R2 space, not just the bit that's shown here, but rotate the whole lattice, but keep the projection the same. And that somehow is what he's saying avoids it.
Yeah.
I still don't know, but really, I'm not an expert for this stuff. So maybe just to rephrase one of the ideas of Dima, you said this stuff, you take n points and then take all these n rotations and take unions and stuff like that. Is something like that analyzed for other point sets? Does this help in some settings?
I actually tried exactly the same thing for spiral points, and it didn't look too promising. But again, this was a special point. It doesn't mean it's not working or whatever. It's just you lose a lot of structure by doing this, right? I mean, what you want to avoid is a square root of an error. So you have to have the same order of rotated copies, basically, or something similar. And yeah, it just looks chaotic. I mean, in my mind at least. I mean, I haven't projected.
No, sure. But what I have in mind is just you say that you have a problem if you have a cap which is aligned with your North Pole to some extent. That's a problem, right? And if you now take the union of n different orientations of the same point set you have, then actually only a very small number of point sets has a problem with this specific cap, because all the others are looking in another direction, right? And this was just what I get some intuition. If I want to learn all the caps, maybe that's not the worst idea. Yeah, never mind. Thanks for answering.
Sure, thank you. Any more questions?
I
Yes,
have a
please.
question. Yes.
Please.
About the tessellation. So it is
Mhm.
equal area, right?
Yes.
Okay. And do you have some guess on the diameter of the pieces? So whether they are of order n to the -1/2, and if this may be hard or
Well,
easy to show?
The diameters, I believe, are n to the -1/2, and it has already been shown in a paper by Saf, Hardin, and I don't know if there was a third order, but it's a comparison of point distribution. It's a
Ah,
comparison of popular point distributions on SO2, and I believe in the Dolomite journal, something like this.
okay, yeah. And can one then show a bound on the spherical cap discrepancy by using something like what you showed us with the lattice and the convex set?
Mhm.
I mean, the spherical cap has the diameter or length at most a constant. And for each of the single pieces of the tessellation, you have 1 point. So only the pieces of the tessellation that intersect the boundary of a cap matter. And this should be bounded by n to the -1/2. Can that be correct?
Okay.
Or am I missing something? Because
It's actually,
I wonder.
so you do it directly on the sphere, right?
Yeah.
But how do you argue how many points? You mean, okay. I have to think about this actually.
Okay.
It seems like a reasonable thing to do.
Yeah.
Yes,
Okay,
it's a
yeah.
reasonable thing to do. Thank you. Yes. I have to think about it.
Any other questions? Well, I'll stop the recording.